To go through the Level 3 Physics 2021 Electricity Examination paper. The best thing for you to do is try this paper out first on your own and then go to check your answers with what I've got. Okay, so question 1 is on alternating current. Kate is experimenting with LCR circuits. She uses a signal generator and connects an inductor, a 1 times 10 to the power of negative 4 farads capacitor. So this is the capacitance of the capacitor, and a lamp to act as a resistor, all in series as shown in the diagram and photograph below. Kate adjusts the frequency of the signal generator until the lamp glows brightly. So when you see the lamp glows brightly, the term that should come to your head is the word resonance. Okay? So that's when the lamp grows brightest. The lamp is brightest at a particular frequency called the resonant frequency. State one condition for resonance to occur. You only need one condition, but I've listed a whole lot of them. Any one of them is good enough, and that's an achieved. Kate observes that the resonant frequency is 2.10 times 10 to the power of 2 hertz or 210 hertz. So by first showing that the reactance of the capacitor is 7.58 ohms, calculate the inductance of the inductor. Okay, so the first thing we need to do is the reactance of the capacitor. Your formula sheet has XC is 1 over omega C, where omega is 2 pi f. So XC becomes 1 over 2 pi fc. Substitute values. Write down the unrounded answers because that's what markers look for, and then write the required rounded answer. If you just got that much, that's an achieved. If you went on further and said that at resonance, these values are the same, so XL will also be 7.58, and so XL is omega L, so you get the value for the inductance of the inductor by substituting, and you get 5.74, and that is merit, and it's 5.74 Henry. Okay, so you want that there. Okay, the next one. While the lamp is at maximum brightness, Kate inserts some iron rods into the core of the inductor. Now state how inserting the iron rods affects the inductance of the inductor. So what's going to happen is that the inductance of the inductor will increase, and if you just got that much and nothing else, because this has got different parts, you get an achieved. Now explain how the change in inductance will affect the brightness of the lamp. So if the inductance increases, then the reactance will increase. Okay. Now if the reactance of the capacitor does not change, it's only the reactance of the inductor that's changing. So XL becomes greater than XC. So as a result, the impedance increases. Now if the impedance increases, then the current is going to decrease, because I is Vs over Z. So if the current is going to be less, then the circuit is no longer at resonance, and so the current will no longer be a maximum, and the lamp will not glow as bright as it was before. So if you've got all these things, you get your excellence. Moving on. With the iron rods inserted in the solenoid, there is a 17-degree phase difference between the supply voltage, which is 12 volts RMS, and the 210 hertz, that's your frequency, and the circuit current. Now what does Kate do? She connects a voltmeter across both these components. Okay, and what do we have to do? What does this voltmeter read? Now, in order to find out what this voltmeter reads is you've got to do a phasor diagram. So these are all 90 degrees out of phase. So your voltage across a resistor is customarily drawn as your horizontal line. Voltage across the capacitor lags that by 90. Voltage across the inductor leads. Now make sure the inductor voltage is bigger, because the reactance of the inductor was bigger, so that's smaller. So you get VL minus VC, which is the difference between these two. Now, so you complete this parallelogram, and this diagonal will give you your supply voltage, which is 12 volts. So you know the 12 volts, you know your 17 degrees, you just have to get this little bit. So the way you do that is sine 17 is this VL minus VC, that's what the voltmeter reads. And this is your hypotenuse, which is 12 volts, and that's how you get your VL minus VC is 3.551 volts. And in this condition, your supply voltage is actually leading the circuit current, okay? Or the circuit current lags the supply voltage. If you got both those, you get your merit. Moving on to question 2. This is about inductors and lamps in DC circuits. So Kate uses a 12-volt DC battery with negligible internal resistance to connect a lamp in series with an ideal inductor whose inductance is 1.60 Henry. And what does she do? She's observing the brightness of the lamp in the circuit as she closes the switch. This question assumes the resistance of the lamp is the same for all voltages. First question is show that the time constant of the circuit with the inductor and the lamp is 0.200 seconds. So in order to show time constant in an inductor resistor circuit is L over R. First got to figure out what is R. We know the L. So how do you get the R? So you look at these values here. So this is your power, this is your voltage. So power is voltage times current. You get your current, and then V is equal to IR, and you get your value for R. And then the last step, your time constant is L over R, and you get the required answer. So that's a 2-step answer. So that moves on to merit. The next one goes all the way up to excellence. So in the space below, draw a graph of voltage against time for the lamp. So there's your lamp voltage, starting at the instant the switch is closed. So now your time constant is multiples of 0.200 seconds. So what I've done is I've done just a little table. So these are your time constants starting from 0 and the value for the time for each of them. And to begin with, the voltage across the lamp is 0. And now this is, before I started doing it, I did this little sketch to tell me what the shape of the graph should be, because it's an increasing voltage. So after one time constant, it's 12 times 1 minus e to the power of -1. This is the easiest way of doing it. You get 7.58. Similarly, you get all your other values for time constant. Make sure you plot your points correctly and you get a smooth curve joining it. If you have everything right, you get your excellence. Moving on, explain the reason for the shape of the graph that you have drawn for the lamp in part 1 and discuss how the inductor affects the voltage across the lamp and comment on the gradient of your graph. So this goes to merit, but it's quite a long answer though. So when you're looking at the graph, it's quite steep at the start and then it becomes less steep as it goes on. So that's what I've described in the first part. So there's a rapid increase in voltage across the lamp at the start and then it kind of slows down. The increments are smaller. Now, the presence of the inductor in the circuit has an effect on the brightness of the lamp. So when the switch is closed, there will be an increasing current. Increasing current. When there's an increasing current or a changing current, there's going to be a changing flux, or in this case, an increasing flux. Whenever there's a changing flux, there will be an induced voltage. So you need to have this in the correct sequence. You first have your increasing current, then you have your increasing flux, and a result of this is the induced voltage across the inductor that opposes or acts against the rise in circuit current. So it takes a while for the current to reach maximum, and the voltage across the lamp is 0 at the start, and by the end of almost 5 time constant, it reaches full brightness as it approaches your 12 volts. Okay, next question. This was an achieved question. What's the energy stored in the inductor once the current is steady? For this, you need to know what is the maximum current, which we found in part A, or if you did not, this is how you get your maximum current using P equals V times I, and you get the I. And so EP is half Li squared, so this is your L, that's your I squared, and you get the answer. Moving on, next one is batteries and internal resistance. So Joel is experimenting measuring the terminal voltage across a battery and the current drawn from the battery when adding lamps in parallel. He notices that the terminal voltage decreases as he adds more and more lamps in parallel, and he uses the data he gathers to plot a graph of terminal voltage against the across a battery against circuit current. So this is your terminal voltage, which is the voltage across the terminals of a cell when there is a current flowing, and you kind of get something with a negative slope. So state the physical meaning of the term EMF. So there are two possible answers. It's the voltage across the terminals of the battery when there's no current flowing, or it's also the energy gained by each coulomb of charge that enters the battery. Okay. Using the graph, what's the EMF of the battery and the internal resistance? So what you need to do is take a ruler, extend the graph till it cuts the y-axis, and that's your EMF. And the gradient of the graph will be your internal resistance. So that's what I've done. So the EMF is nearly 9 volts. It's about 8.9, and there's your resistance. And show you're working clearly. Now explain why the terminal voltage of the battery decreases as more and more lamps are added in parallel. So when you have more lamps in parallel, the total or effective resistance decreases. If the effective resistance decreases, then the current drawn from the battery increases. So if there's greater current drawn from the battery, then your voltage drop across the internal resistance, which is I times R, increases, because that increases, that stays the same. So your terminal voltage decreases because it's a difference between the EMF and the voltage drop across the internal resistance. Then Joel repeats his experiment using a different battery, but it becomes flat before he has finished. He recharges it using the circuit below. So this is your flat battery, which is rechargeable, and this is your charger. Using the information in the circuit above, calculate the current in each of the 3 branches using Kirchhoff's laws or any other method. Begin your answer by writing the equation for the current for all those 3 currents. So current at a junction, the current entering the junction is the same as the current leaving it. This is the only one that's entering. Those 2 are leaving. So that's how you get I3 equals I1 plus I2. And then to make it easy, I just labeled the corners. So I started with that loop. It doesn't matter which loop you start with, anyone. So I started with this loop and going anti-clockwise. So when you come out of the positive end of the battery, I put a plus sign, so 8.50. And then you're going with the current. So current carries more energy before entering the resistor. So it's minus 2.90, which is the resistance times current is voltage. So 2.90 times I2, and I got the value for I2. Now I know what's the voltage across this. Now I'd get the next loop here. Now in the top loop, you have, so I started from here, and I'm going anti-clockwise, so it has more energy when you're kind of going through. So it's 2.90 times 2.93, so resistance times current is voltage. And then I'm going out of the negative terminal, so that's why I got the minus 6. And I'm going with the current, or the current has less energy when it comes out of the resistor there. So you get minus that, and that's how you get your answer for I1. And then I go back to this equation to get my I3. So once you get all the 3 currents, you get your excellence, and that's this paper.